What if y is natural log of x? You need to know what the base of that is. What's the base of the natural log? E, right? So that means the derivative of this will be 1 over x times natural log of what? E, right? But wait a minute, what did we just say the natural log of E was? 1. The natural log of E is 1. So in this particular case, in this case only, this is a very special case, that's just 1 over x. And that's one you should, as quickly as possible, memorize. Right? If you take the natural log of x and you take its derivative, you just get 1 over x. That's on your sheets as well. It's when the base is something other than e that you actually have to include that natural log in there. Here's another one. What about log of x? What's the derivative of that? What's the base of this one? 10, right? So it should just be 1 over x times natural log of 10. And unfortunately, natural log of 10 is not 1, so we're just going to leave it there. That's just some number. We don't know exactly what it is. We get on our calculator and figure it out. All right. Any questions? So as soon as I give you a new formula for a new derivative and you understand it, which you're saying you understand this? Yeah. Now we need to be able to use this with all the other rules that we've already learned. So that means we need to be able to throw in product rule, quotient rule, chain rule, all that stuff. We need to be able to throw this into the playing field. So let's do something like this. What if we have y is, I don't know, x cubed natural log x? Find y prime. So what would you have to do here? Product rule. Right? Y'all see the product? It's between the x cubed and the natural log of x. Let's go ahead and do it. So I do derivative of the first one times the second plus derivative of the second times the first, right? 3x squared times natural log x. That's the derivative of the first one times second. Why am I not doing implicit again? Because it's solved for y, right? It is solved for y. So because it's solved for y, only the left side gets the dy dx. Everything else here, any chain rule I ever do, I'm going to get dx dx, which turns into 1s. So that's why I'm not even paying attention to it anymore. I'm not done though, right? Plus, now, derivative of natural log of x. 1 over x. And then times the first function, like that. Yeah, I'm going to simplify that. That's 3x squared natural log x plus that becomes just x squared. Oops, x squared, right? Yeah, x cubed over x.
So to like put it simply, you would use the implicit rule
when you have x's and y's mixed together and you can never get y by itself.
Okay.
Which if you go back and look at all the homework problems from implicit, that's the way they looked. Or if you're doing a related rate problem. Because with related rates, we're usually differentiating with respect to time, which isn't even in the equations, right? So you have to do implicit. All right, how about this one?
Oh, that's the answer?
Yeah, I mean, you could factor out an x squared if you want. I mean, you don't need to, but you could pull an x squared out, but that doesn't make it any more right. It was right as soon as we cleaned it up right here. All right, how about this one? How about log base 4 cubed of x, like that? Chain rule, right? That expression, we need to understand, really means that, right? That's what that means. That third power right here means that we're cubing the entire logarithm. So to differentiate this, I need to do a chain. So the 3 will come out, right? 3 comes out. Then it's all of this squared, isn't it? I'm going to write that this way. You'll see what I've done? 3 comes out. All of this squared would just be this. Am I done? No, I've only done the outside, right? I've only done the cubed. Now I need to take derivative of what's in here. And that's what we started with. Y'all said y'all were comfortable with this. The derivative of log base 4 of x is just 1 over x times natural log of 4. Look back in your notes. We did a problem just like this, right? That's pretty much it. Not a whole lot I can do with that. I mean, I could put all this up top here, but nothing like cancels out.
Do we have to memorize the 1 over x ln number or a?
Well, do you have to? I mean, it's on your formula sheet. Yeah, it is there. It's on the derivatives formulas. Yep, you're there. It should be right there. What number is that? Formula 12?
12 on page 5.
Yeah, 12 on reference page 5. All right, how about this one? How about this one? Y is log base 4 x cubed. Is that the same problem we just did? No, why not?
Because you have to multiply the x is log 4.
Yeah, the cubed is on the x, right? Not on the entire logarithm? Is it still chain rule?
Yes.
What's the outer function? Log, right? Log base 4, and then inside of that is x cubed, right? So if I'm going to use chain rule, then what I would do is I'd start out and be real careful here, all right? Because this is where things can get a little messy. We're doing the derivative of log base 4 of my eraser, right? What is the derivative of log base 4 of my eraser? 1 over my eraser, right? Which is x cubed times natural log 4, right? That's the derivative of log base 4 of my eraser. The derivative of that is 1 over my eraser times natural log of 4. But I'm not done, right? Now I need to multiply that by the derivative of what's in here, which is what? 3x squared. And there's still more I can do. I can put the 3x squared on top, and there's still more I can do.
Reduce the x.
Yeah, we can cancel out some of those x's, can't we? If I kill off these two, that would leave me with just 1 down there, wouldn't it? So I could have put here 3 over x natural log 4, right? Any questions there?
Which would
So-
you count?
Which would I count?
Correct. Would you count?
Well, they're technically they're both right. Like I couldn't take off and tell you that's wrong, right?
Yeah.
I could only say it's not simplified, right? But it's not wrong.
So you could use the logarithmic rule to just pull the exponent out.
Yeah, so good.
And then that'll
Yeah,
behind.
I'm glad you saw that because I was just going to say this. At the very beginning of the problem, if you would have realized that we've got log base 4 of something to a power, right? The property of logs says I could pull that 3 out, right? Before I take a derivative, I could have rewritten this as y equals 3 log base 4 of just x, right? That is just the property of logs. I said that was the one that was really important that we would use, right? Now, if I ask you to take the derivative of this, The 3 comes for the ride, right, because it's a constant attached in front. And now you're just taking the derivative of that, which we already have seen is just 1 over x times natural log 4, right? And do you see if I slide that 3 back up top, we get the same answer, which we should, right? I mean, this is math. It should work no matter how we do it. As you might imagine, you can do, like, anything you can think of that has logs in it now can be a problem. You just need to know, am I doing quotient rule, chain rule, product rule, right? So you're going to need to practice the homework for this because there's a wide variety of things to look at, all right? Let's do one more example. How about the square root of natural log of x sine x? I want the derivative. All right, first things first. I know some of you might be thinking, okay, hey, the square root is really the 1/2 power, right? And then I can maybe pull that 1/2 out. You can't, because the property we have of log says this. If you have log base a of x to the r, then the r can come out, but that r has to be acting on the x alone. If you rewrite this as a power, it's going to look like this. X sine x, all of that to the half, right? The half power is not just acting on what's inside the log. So you would not be able to pull that out. Like, you couldn't use this property. Don't understand what I'm saying? So I'm not going to do this either. I'm going to go back and I'm going to go back to my rag here, and I'm going to use chain rule, right? I got square root of this, right? What's the derivative of the square root of something? 1 over 2 square roots of whatever was in there, right? And what's in there? ln of x sine x.
Does that need to be parentheses? Oh,
This
part of that.
it doesn't, well, you could argue with me if it's not in parentheses, right? If it's not, you could argue with me that this is that, which it is not. I'm not saying natural log of x times sine x. I'm saying natural log of x times sine x. So yeah, you'd want that in parentheses for sure. Am I done? No. Now I need to say times, because I'm doing chain rule. I've already taken care of the square root. Now I take the derivative of the natural log of something, right? Derivative of the natural log of something is 1 over that something, right? 1 over, not x, because x was actually this whole eraser, right? Natural log of my eraser, the derivative of that would be 1 over the eraser. See, that's different. We haven't had one like that before, have we? But do you understand what I'm doing? It's just chain again. The natural log of something, derivative of natural log of something is 1 over that something. Am I done? No, got to go inside. Done with the natural log. Now I have to say times, now the derivative of this. And how do I do that? Product rule, which means I need a set of parentheses, because I'm going to get 2 pieces here. I'm going to get 1 times sine x plus cosine x times x. So that's the derivative of the first one times the second plus the derivative of the second times the first. Yeah, I mean, sine x. You can't, I'm not sure what you're saying, but you can't put this in this root. If I were to just get a final answer here, here's what I would do. I take all this and just put it on top. Sine x plus x cosine x over, so that's this right here. Now on the bottom, I just leave this. I would go to something like 2x sine x square root of natural log of x sine x. That's about all I can do. Just move this out in front right here near the 2. Slide all that up top. Now, I told you you're going to need to practice, right? And this homework assignment for 3-3 gives you a lot of problems to practice. I told you what the derivative of a log was, right? And I asked you to take it off. Hey, what's wrong? You all right? You okay? What's wrong? You got a question? What's your question?
I'm wondering where you got the X right next to this cube.
Right here. Right there. I just took this and I just put it right there.
Got it.
Yeah. I didn't have to do that. I just did. I don't like to put things behind roots because I don't want people to accidentally think that it's actually under the root. So if I put it out in front, there's no, you know, some people will actually do this with their roots at the end. They'll do that, and then they'll put a little mark like that, and that tells you where it stops, and that way you don't accidentally take something behind it and push it in there. All right, so I said the derivative of a log, here it is, take it on faith, right? Now we're going to talk about the derivative of an exponential function. And for this one, I'm actually going to prove it to you, but not with the limit proof. I'm going to prove it using what we just did, all right? So this one I'm going to work on. I'm going to show you. So if we have y equals a to the x, right? If y is a to the x, and I ask you to find y prime, then right now you don't know what the derivative of that is, right? You don't know. What you do know is this, because I told you to believe me, and you said, okay, I'll believe you, but that's 1 over x ln a, right? That one. That's good. That one, though, I want what the derivative. So what I'm going to do to prove this to you, without telling you to take it on faith, is I'm going to come in and I'm going to take the log base a on both sides of this equation. And the reason I'm doing that is because I know that on the right-hand side, if I do log base a of a to the x, what happens? It cancels and you just get x. So this right side is x, and the left side is log base a of y, sorry, not of x. Do y'all agree with that? I'm just doing some algebra there. Now, I'm asking for us to find y prime, right? Remember, this is dy dx. I am going to use implicit here, but only because I'm trying to prove this to you, all right? We won't be using implicit anymore when we do like examples. I'm just trying to show you what the derivative of a to the x is. So I'd like for you right now to take the derivative implicitly on both sides with respect to x. So the derivative with respect to x of the left equals the derivative with respect to x of the right side. So which of those sides looks nicer to you? Right side. What's the right side? 1, right? That's just 1. So the right side is 1. Now, be very careful. What is the derivative with respect to x of log base a of y? So it's 1 over y ln of a, right? That's what this, the derivative of this would be 1 over y, natural log of a, but you have chain rule still. What's the derivative of y with respect to x? dy dx. So you still have a dy dx next to this. And that's great because that's what I'm solving for. Y'all all right with that? Run through it one more time. Derivative, that's just 1. This one over here, derivative of log base a of y is 1 over y natural log a. But then I take derivative of what was in the log, which is y, and with respect to derivative of y with respect to x is not 1, it's dy dx. And that's what I'm solving for. So how about this next line? Do y'all buy that? I just multiply both sides by y natural log a. So y natural log a here, canceled. Y natural log a times 1 is that. And now finally, wait a minute, hold on. What is y? What was y in the very beginning of the problem? A to the x. That's your answer. The derivative of a to the x is what? Itself times natural log of a. That's the formula, and that's in your formula sheets.
What happens if A is E?
Yeah, so what happens if a is e? Well, let me get to that. Let me do another one first. So as an example, if I said, hey, here's 4 to the x, what's its derivative? You would say what? Itself first, right? Itself is just 4 to the x, but then times natural log of 4, and you're done. I had a student do this. Tell me what they did. Tell me if it's right. What did that student do? They tried to do the power rule, didn't they? They were like, hey, I've got something to a power. I'm going to bring the power out, and then I'm going to subtract 1 from the power. That is completely wrong, because the power rule only works when x is in the base and the power is a number. Then, yes, the power comes out, you subtract 1 from the power. That is correct when the variable's here and the number's here. But when they're reversed and the variable's here and the number's here, then it doesn't follow the power rule. It follows this rule. All right?
Is there a name for this rule?
I don't think there's a name, just derivative of exponential function. Okay, so this is wrong. All right, let me do this one. What is the derivative of 10 to the x? So I look at that, I'm like, hey, that's a to the x, right? So it should be itself times natural log 10. And now the question, what about e to the x? What if you have e to the x and you take its derivative? You get itself, right? E to the x, you get itself, and then times, this is the key, natural log of what? E, but what's natural log of e? What's ln of e? 1. So this is e to the x times 1, which is itself. And that is the only function that does that. The only function that exists that is its own derivative is that. Is e to the x. All right, I'm going to put something on the board here. You are allowed to add this to your formula sheets if you want, all right? You don't have to, but you can. There's not much that I allow you to add to it, but this one you can. I'm going to do a quick summary of everything we've just done here in terms of exponential and logs and their derivatives, but in a slightly different manner. Here's the way I think you should think about it. Let's say that you have log base A, and inside of it you have some box. All right? Who cares what it is? And you want the derivative. What's going to happen first is you're going to say, all right, that's just 1 over whatever that box is times natural log of A. But then chain rule is going to tell you to multiply that times the derivative of what was in that box. Do y'all see how that works? Or it's like if you have log base A of something, the eraser, the answer is 1 over the eraser times natural log of A, but then you still have to take derivative of the eraser. That's your chain rule happening. I hope that makes sense to everyone. Now, let's look at one of the special ones. If we have the natural log of a box, right, and we take the derivative of that, well, that should just be 1 over the box, right? And then this part is the part that becomes natural log of e, which we already know turns into 1, right? And so I don't have to worry about that, but then I still have to do chain rule, which is the derivative of the box. So you get 1 over the box times the derivative of the box. And some professors, some books just do it this way. That in this very special case that we have natural log of something, the derivative of natural log of something is just the derivative of the something over itself. You see that ratio? All right, that's for logs. Those are like the 2 generic formulas for logs. Now let's look at the a's, the exponentials. If you have a raised to a box and you want to take the derivative, it's going to be a raised to whatever that box is. Then you always have to tack on a natural log of a. And then you're not done. You have to take derivative of whatever was up there. And in the special case that it's e to a box, we would get e to the box. The natural log of e would be a 1 right there, so I don't need to write it. But next to it, I'd still have times the derivative of the box. That's like a generic symbolic representation of how you incorporate the chain rule into differentiating exponentials and logs. Now, I hadn't done any examples of these like harder ones, so let me just show you an example of this one. Let's say we had 4 to the x sine x, and I want its derivative. Do y'all see that that's a to a box? The box is x sine x, right? So according to the formula, the derivative of this will be first itself, right? I just rewrite what it is. Then I have to tack onto it times natural log of 4, because that was my base. But then next to that, what do I need? The derivative of what was up there, which is going to require product rule, right? And so I need to throw that in parentheses, and I'm going to go off camera, but it's okay. So the derivative of what's in there was 1 times sine x plus cosine x times x. That's the derivative. This has to be in parentheses. I know on some of you that took the quiz last time, some of you got 98, so sorry. I feel bad taking off, but if you don't have the parentheses, it's not right, because there's a big difference between, I think I showed you all this already, there's a difference between me saying 4 times 3 plus 2, right? There's a big difference between that and 4 times 3 plus 2. Right? Those don't give you the same answers. So if you're going to say you're going to multiply by something and that turns into 2 things, then this would have to distribute through. So I need the parentheses there. All right, let's do one with e. What if we have e to the square root of x? What's its derivative? E to the square root of x times, now the derivative square root of x, right? Which is just 1 over 2 root x. Hey, can I cancel these? No, absolutely not, right? That root x is up in the exponent. So yeah, I mean, maybe you could do a little more. I mean, this is fine as an answer for me, but the most you could maybe do is this. You know, just slide that underneath. Do y'all find this helpful at all? Like this, like with the boxes? Yeah. A lot of times books will do it this way. Instead of using a box, they'll put like u here, then this is u, and then they'll put u prime there. Or they'll put u here, and then they'll put u here, and they'll put u prime. Or sometimes they'll put du.
What is it that we were supposed to put on the formula sheets?
Everything I put right there, all of this.
Those are just formulas, right?
Yeah, they're just formulas. But those formulas kind of stress the chain rule is there, right? These help you not forget chain rule. Because what will happen is I'll get students that you know, they'll get to a test or something, they'll be all panicked because it's test, and they'll do something like this, like e to the x squared, and they'll go to take the derivative, and they're like, oh, I remember, the derivative, that's just itself. That's not right, right? What are you missing? Times 2x. You're missing times 2x because the derivative of e to something is itself times the derivative of what's up there. Now, if it's just e to the x, then yeah, I agree the answer is e to the x, but the reason why is because when I go to take derivative of what's up here, what's the derivative of what's up here? 1, so this is times 1, so it is itself. Okay, I need you to practice and do some problems. Try and decide how I want to do this, but I'm going to show you one last thing. So have you all heard the expression, like, don't get the carriage in front of the horses? Have you all heard that expression before? You know, you have horses and then you have the carriage. Horses, then the carriage. Don't get the carriage in front of the horses. Like, that's not the way it works, right? So I don't mean to get the carriage in front of the horses here, but it's a cool result that I can share with you from Cal 2 that will kind of maybe make you curious a little bit about Cal 2, but then also it'll show you a better proof of why e to the x is the derivative of e to the x is itself. So in Cal 2, we can prove this is true. That e to the x is, oops, not plus. E to the x is equal to 1 plus x squared over 2 plus x cubed over 3 times 2 plus x to the 4th over 4 times 3 times 2 plus x to the 5th over 5 times 4 times 3 times 2 plus, and guess what? This goes forever, okay? And for those of you who have seen this before, you all may know that these right here is another way we can write that. We can write it as 6 factorial. If you've ever seen that symbol before, 6 factorial. This is 5 factorial. This is 4 factorial. This is 3 factorial. This is actually 2 factorial. And then there's a 1 under there, and that's not important. I'm just sharing that notation. So this goes on forever. What I'm telling you is that e raised to any power is just a polynomial. Do you all see that this is just powers of x? But it's an infinite polynomial. It's a polynomial that goes forever, which at this stage in our mathematical lives, we've never even talked about infinite polynomials. We've only talked about finite polynomials. So in Cal 2, we learn, is one of the big results in Cal 2, that pretty much every function you've ever learned in your life can be written as an infinite polynomial. And what's great about that infinite polynomial is that we can do lots of cool calculus with it easily, easy cool calculus.